casual conversations about science with the scientists themselves. It's the place to be to talk science. This is Coffee and Science with your host, Rob Parks.
Howdy all, and welcome to Coffee and Science with your host, Rob. Before I begin, I'd like to take a moment to remember a certain individual who unfortunately passed on last night. That individual is, if you are not a member of our community and have not heard, that member is Cliff Overby, aka Schrodinger's cat. He has had a fairly successful channel, and he is a large member of our community, and he will be dearly missed. He was a husband, a father, and a sailor. And wherever he is, I wish him fair weather, and my heart goes out to his friends and family. Okay. Well, today you are going to be entertained by only by myself for two reasons. One, primarily one, I was a bit lax to follow up with a few folks that I hope to have lined up within the next couple of weeks. And the primary reasons were semester is starting up and health reasons and so forth. So you're basically just stuck with me at the moment. But what we are going to be talking about today is JWST and space telescopes in general. And what I'd like to do is really just kind of summarize the history of what NASA refers to as the great observatories, and touch upon the next generation great observatories, and talk about not only what they will be able to do, but also talk about a glaring problem that the astronomical community is going to have moving forward. And so you'll have to excuse me. I should have prepared a script, but blah, 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 blah. Before I begin, what I'd like to do is, before I get into all this, what I really want to touch on is what astronomers refer to, and I guess physicists refer to, as the electromagnetic spectrum. This is key to understand when you were talking about telescopes and space observatories, because what wavelengths that they can observe essentially dictate what sort of astrophysical phenomenon they can study. The electromagnetic spectrum is a very fancy term for all wavelengths of light. And it ranges from the most energetic light that you can possibly observe, the gamma ray spectrum. Then you move into the X-rays, moving from high energy to low energy. You have gamma rays, then X-rays, then ultraviolet, then visible. And visible is the only biologically defined range in the electromagnetic spectrum, and as such, it is actually the narrowest by far of the, I believe, 6 different regions, 7 depending on how you count it, is our human eye can only resolve or only see around 400 nanometers to about 800, 900 nanometers. Now, nanometers, for the uninitiated, is 10 to the negative 9 meters, or 1 over 1 billion meters. We're talking about a very, very small wavelength. I should probably say hello to all, to Tusk, to Dora, and Professor Phil Bell. Thank you for coming by. So where was I? The visible spectrum, 400 to roughly 900 nanometers. from blue to red. Like I said, a nanometer is one billionth uh, of a meter. Another measurement that we're going to be using is a micron or micrometer. That moves into the infrared part of the spectrum, or the redder or less energetic part of the spectrum beyond visible. Now, colloquially, that is primarily referred to as heat. Now, heat is actually just light. It is infrared light, and it is in the micron range of wavelengths. And a micron is one millionth or 1/1 millionth million meters. So also very small. We're talking about very, very basically, I was going to say dust grains, but that doesn't really help. I believe bacterium are about that. Bacteria are about that size. So you can conceptualize how small that is. You go from the infrared, which, like I said, is heat, and then that moves into radio. Now, something to keep in mind, and something that becomes rather important when we're talking about space observatory, is the atmosphere. We have this wonderfully protective atmosphere that allows us to exist, because if the atmosphere weren't here, gamma rays and X-rays, unfortunately, gamma rays do not turn you into a giant green rage monster. They just kill you, and do so on a fairly quick time scale. X-rays, in abundance, are also deadly, and ultraviolet in abundance is very deadly. But thankfully, our atmosphere, for the most part, it completely blocks out gamma and X-ray and most of the ultraviolet. So the scenario, or the position that puts astronomers in, if we want to study in the gamma ray X-ray regime, we have to put telescopes in orbit. Or there have been some successful observatories that actually have that are part of a high flying balloon, or deployed by a high flying balloon, but that's problematic in itself, because the length of the mission is fairly small. There's only a small amount of time that balloon can float up there in the sky. So if we really want to do detailed studies of the gamma ray or high energy astrophysical phenomenon, we have to put telescopes in orbit. So that's basically the electromagnetic spectrum in brief. I was hoping to have a diagram of it, but if you Google electromagnetic spectrum, I'm sure you could find an example of that. Now, the great observatories, let me see if I can find a picture of it. The great observatories were 4 in number. Now, in the 1990s, well, let me back up a second and say that the way that astronomy progresses, or at least this way that funding progresses, is that every decade since the 1970s, astronomers get together and decide what's cool, what's sexy, what do we want to focus our attention for the next 10 years. And these are referred to as decadal surveys. So in I think it was the 1980s, typically it's about a 10-year lag. In the 1980s, there was a large push in the decadal survey for space telescopes, specifically in the X-ray and gamma ray regimes, because those are essentially undiscovered or unstudied regions of astronomy. So in the 1990s, NASA took that idea, and at this point, NASA was in a mode called faster, better, cheaper. I think that was the slogan that they did. They were very interested in smaller programs, smaller missions that could be built quickly and built on a reasonable cost. Thankfully, during this time, 4 major observatories, space observatories, were built. You have the Compton Gamma Ray Observatory, you have the Chandra X-ray Observatory, the Hubble Space Telescope, and Spitzer. These I'll go over briefly what each of these did, the specific specifications, as it were. But it pretty much completely covered the range from gamma ray down to infrared. As far as I know, there's never been a space radio telescope, but for various factors, really, it's impractical to actually have a radio dish in space because in order for it to be able to see with any sort of precision, the thing would have to be gigantic, and that's just not technically feasible. But anyway, the four major observatories, Compton, Chandra, Hubble, and Spitzer, were all launched in the 1990s and 2000s, and they dominated the high precision observatories in terms of the science. Now, let's see here. Let me start off with the Compton Observatory. Ooh, I have a picture of it somewhere. There it is. Yep, that's not what I wanted to do. That's what I wanted to do. The Compton Observatory was launched and was actually, I believe, the first one launched, and it was launched in April 5th of 1991 aboard the space shuttle Atlantis. And as you can see here, it's actually hasn't been fully deployed yet, but I couldn't really didn't have the time to actually find a fully deployed picture of Compton. It has since deorbited. It was deliberately the telescope had run its course and was no longer functional as a scientific instrument, and so instead of just leaving it up in space where it would be space junk and potentially slam into something important, it was purposely deorbited, meaning that it was put into a controlled deorbit or basically trajectory towards the Earth, and it splashed down in the ocean. And this was done on June 4th, 2000. Primarily, one of the reasons why it was done was it lost one of its gyros. Now, very quickly, space telescopes typically have 3 gyroscopes on them. Due to the concept of angular momentum or conservation of angular momentum, by spinning gyros, you have various gyros, you can cause the telescope to move in all 3 directions. With Compton, one of the gyros failed, and so it couldn't point in a particular region of the sky, and so it was felt that it had already achieved its science goals, and there was no point in trying to continue with it at that point. Now, the wavelengths here, like I said, are in gamma rays. Specifically, the instruments that were used went from 30 keV to 30 gigavolts, or GeV. EV is electron volts. It's just take my word for it. It just means really high energy. Now, some of the notable things that Compton was able to do was that, let's see, I believe I have a picture of this, is that it studied gamma ray bursts. Now, gamma ray bursts is a astrophysical phenomenon that ranges from signals that we see from milliseconds, they last milliseconds, to upwards of a few minutes. Now, depending on the timescales that we're looking at, that informs us as to what's actually causing these things. And gamma ray bursts can be caused by basically accreting matter onto neutron stars is the most common most common cause for a gamma ray burst. Is you have a massive amount of material that falls onto a neutron star, and it just creates a very, very energetic event, and a brief burst of energy can be seen. And Compton was able to map out the entire sky, and it allowed us to see that gamma ray bursts are uniformly distributed around the sky, which was important because previously because again, we didn't have really we didn't have a method to detect these things. It was believed that gamma ray bursts were only constrained within our own galaxy. This map shows us that no, in fact, these are exceedingly energetic, exceedingly luminous events, because we can see them in galaxies, in faraway galaxies. That even distribution means that we are seeing events from an evenly distributed background of galaxies. Now, more recently, gamma ray bursts have been tied to black hole mergers and black hole neutron star mergers. And so, again, gamma ray bursts are something that is very important to astronomers, particularly in the age of LIGO, where we have the ability to actually resolve, or with gravitational waves, we can detect single or very low mass black holes slamming into each other, or a black hole and a neutron star slamming into each other, which the first one was detected, I believe, in 2017 or 2018. So it's a very, very small, or very, very young, very, very young field of study. The other thing that it was able to do was that it actually created all sky maps of galactic radioactivity, and looking at antimatter concentrations within our galactic center. Again, these studies can only be done with this particular type of telescope. Now, the next would be Chandra, which was in the X-rays, which you can see here. Chandra was launched in July of 1999 aboard the Space Shuttle Columbia, back in the good old days when we actually had, space shuttles rather than phallic delivery systems. Chandra is still in orbit. It is still in active service, and although it is now approaching 30 years of service, so I'm not an X-ray astronomer, so I don't know what condition the telescope is currently in. But Chandra has the distinction of that it's 0.8 its mirror is 0.8 meters in size. To give you a sense of scale, if that is the same size as our telescope here at George Mason. So it's a relatively modestly sized telescope. Again, this is back in the 1990s, 2000s, when putting up a large mirror was complicated. Was an engineering, which is an engineering feat that we hadn't been able to get to yet. But it is the smoothest mirror ever created. To give you an idea, this curvature, or the smoothness of if you were to compare the smoothness of that mirror to, say, the Earth, and you took the Earth and you smoothed it out, the deformations, or the difference in, say, its perfect parabolic shape, would be akin to Pike's Peak would essentially be 1 inch tall. It is my point is that it's an exceedingly smooth mirror. The reason for this is that in order to get good images, a telescope mirror, has to be smooth down to a small fraction of whatever wavelength that you're looking at. So because X-rays are have small wavelengths, the mirror has to be exceedingly smooth in order for it to be useful anyway. The Chandra was primarily used in studies of black holes, supernovae, and dark matter research. With black holes, the reason why, if you look at a black hole, particularly supermassive black holes, they have a large accretion disk surrounding them, and there is basically frictional forces in the very inner part of the disk, which causes a tremendous amount of energy. Yes, Carl, that grinding process must have been. I don't know if it was ground or if it was spun, but yes, that was probably a bear to actually get that done. And then dark matter studies, the way that it studied dark matter is that we can look at, there's a tremendous amount of gas between galaxies and galactic clusters, and that gas has a certain temperature. And that temperature is dictated by how fast that gas is moving. And based on the amount of mass that we can see in the galaxies themselves, that mass is insufficient to be able to move those gas clouds at such a high rate of speed. So there must be dark matter or matter that we cannot see at that location that's causing this gas to have large velocities. Then, of course, we come to the Hubble Space Telescope, which is hopefully everyone knows about, or I would imagine it's a common household name. If you ever heard of a space observatory, you probably have heard of Hubble. It was launched in April 24th in 1990, so I guess it was the first of the great observatories launched aboard the Space Shuttle Discovery, and it is still in service. We actually were able to convince the U.S. government to give NASA enough money so that a rescue or basically a service mission was sent up around the mid 2010s, and actually was able to put in some more coolant and take care of a gyro that had failed, so that its mission can extend towards about 2030 to 2040. They anticipate Hubble to be finally defunct. Its primary mirror is 2.4 meters, so it's a modest for research purposes. It's a modestly sized mirror. To give you a sense of scale, the largest mirrors on the Earth, or for ground-based observatory, we have the Keck telescopes on Mauna Kea. Those are 10 meters in size, so basically a fourth of what Keck is. Hubble is perhaps the most prolific, or is definitely the most prolific space observatory, and is one of the most prolific observatories that we have ever had. It is, like I said, been in service for 30 years. It has 1.5 million observations. If you see any really, really cool, really colorful pictures of galaxies and nebulae and star-forming regions, more than likely, those images were taken with the Hubble in one sense or another. The Hubble telescope is responsible for around 19,000 peer-reviewed papers in astronomy. And so, yes, I think Carl pointed out that when Hubble was first put up, it was actually myopic. There was I believe, and it goes to show, if there are any students who are watching this, and your physics lab instructor harps on units, pay attention, because this is a fine example of this. Basically, if I remember, if memory serves, the reason why the curvature of the mirror was off is because from design to implementation, there were some units missing, and so the basically the angle of curvature was off from the original designs, which actually is won't really go into it, but is actually kind of a good was a benefit, because when it was put up, and there was a period of time, I think it was about a year, they were like, well, we have this very expensive telescope, very powerful telescope in orbit. We can't just not do anything with it. Yes, the images are blurry, but we can't just not do anything with it. So they took observations, and that caused a large surge in image reconstruction, which is something that basically it's algorithms that take blurry images and make them sharper down to the actual angular resolution of the telescope. So if Hubble wasn't myopic, that field of study would probably not have gotten as far along as it is today. is perhaps the most versatile of the great observatories. It ranged from observing in the UV all the way down to the IR, from 100 nanometers down to about 2,500 nanometers, using 6 particular instruments. And it would take too long to really go through all of the astrophysical phenomena that Hubble contributed to. Basically, every phenomenon in science or in astronomy that you can think of, every type of object that you can think of in astronomy, Hubble's looked at it, or has looked at an example of it. Galaxies, solar system object, asteroids, comets, young stars, old stars, black holes, supernovae, that sort of thing. Pretty much looked at everything. And so, like I said, we've gotten 1.5 million observations out of her. We'll continue to get more. And at the moment, it's like 19,000 peer-reviewed papers, which at the moment I believe is, like I said, it's one of the most, if not the most, prolific satellite that we've had. Now, this is a schematic of Hubble. You can see the solar arrays here, and then you see the 6 instruments that you have, or that we have on there. That's not who I want to talk about yet. I don't want to talk about them either. Let's talk about Spitzer. Now, Spitzer is kind of near and dear to my heart because I tend to love infrared astronomy, primarily because I can look at young stars and the history of stellar formation and planetary formation. It was launched on a Delta rocket. It was actually the only one of these that was not launched on a space shuttle. It was launched. It was the last one launched in August of 23, August 23 of 2003. It was decommissioned fairly recently in January 30th of 2020. So it had a very good run. It was not believed to the expected lifetime of the telescope was around 5 to 10 years, which is actually fairly normal, or kind of the best ballpark that we can get. It had to be cooled down because it was looking in the infrared, or basically the heat part of the spectrum. It had to be exceedingly cold. It actually had to be colder than the ambient space. Well, I should back way off that. It had to be very, very cold in order to be used. It observed from 3 to 180 microns, and it was used, like I said, to study young stellar objects, which the youngest of these are heavily embedded in what we call giant molecular clouds or stellar nurseries. And it's just a giant cloud of dust and gas, and they are so thick, as it were, given their size, that if you were to try to look at them optically, if you're trying to look at them using your eye, you wouldn't be able to see it. It would be like looking through dense fog. You wouldn't be able to see those stars at all because they were so deeply embedded. But if you look at the infrared part of the spectrum, you can bypass all of that infrared, or heat will move through that dust and gas far more easily, and you can actually get down into the centers of these things. And hello, Rishi, and actually see these objects. Was perhaps one of the most sexiest parts of the let me zoom in on that. One of the sexiest things that Spitzer could do that no other observatory could do is that we're actually able to look at exoplanet atmospheres with a certain rate of precision. We were able to actually look at exoplanets, and by using a trick where the planet is right in front of the telescope, or just moving just in front of the host star, or just behind the host star, we could actually see observations or get observations of the atmosphere of the planet, if basically by looking at the atmosphere of the host star. I'm hopefully at one point I'm going to do a Rob World episode where I talk about um, exoplanet observations and techniques that we use in order to see these various objects. But as there have been more ground-based observations on exoplanet atmospheres, but again, because Spitzer is in the night sky, it has a advantage over ground-based observations because it doesn't have to worry about contamination of the Earth's atmosphere. And so it was the first time that we're able to actually see this. It was also used to look at AGNs, which are exceedingly powerful energy engines, basically supermassive black holes in the center of galaxies. And it was able to look at some of the youngest galaxies that we have, or that we've. These are galaxies that are about 1 to 4 billion years old or so. Or these are galaxies that formed when the universe, I should say, that were 1 to 4 billion years old. All right. Oh yeah. Hi, Rachie. And so those are the 4 great observatories. And I should also point out that Compton, Chandra, and Hubble were actually orbited around the Earth. Spitzer was the only one of the 4 observatories that did not technically orbit around the Earth. It actually was in a Earth trailing orbit. So it's actually fairly far away. It will not be able to be deorbited when it's decommissioned now. So it's basically just going to hang out where it is in orbit around the sun, and hopefully it won't slam into anything. But it's so far out that it is not a danger to any orbiting satellites or space stations around the Earth at the moment. That's important because that is a concern for observatories moving forward. We need to figure out, or we're looking at avenues of placing telescopes beyond the Earth's orbit, because at the moment, while space is big, admittedly, we are kind of running out of it. There are preferred orbits for various satellite communication, things of that nature, and so things are getting a bit crowded up there. So we need to, for astronomy purposes, we need to find new ways or new locations to place these telescopes. And so we have, like I said, we have those telescopes. We had those telescopes up, and it was a wonderful time to be an astronomer because we had a very large range of observatories to very large. We had these 4 observatories, and depending on what kind of astronomy you wanted to do, you had the opportunity to use one of these space telescopes in order to do the work. Now, why? I don't know if I really stress why space telescopes are important. The reason why is they are beyond the Earth's atmosphere. The Earth's atmosphere, while it does a great job of protecting us, it does kind of a crappy job at allowing us to see the universe. It degrades images, basically causes images to blur out. And so special techniques have to be used in order to get the sharpness or precision that we want with these larger telescopes. And even with those techniques, depending on the size of the telescope, space telescopes actually outperform them. And so that is the reason why we need to put these telescopes in orbit, and why this is so important to astronomy in general. So we had the latest decadal survey. Well, let me back up a second. In 2010, we had another decadal survey, and the 2 primary goals, or the 2 primary sort of subjects that we want money from the government in order to study are, of course, exoplanets and dark energy, dark matter. We want to know we want to know what these things are, and essentially how our universe came into being, and ultimately how it's going to end. Now, out of this was born the concept of JWST, as you probably you've heard of in the news. It has recently been launched. If I've got this was launched on the 25th of December. It was a Christmas present to astronomers in December of 20 on Christmas Day, 2021. And its projected lifetime is around 5 to 10 years. But again, given our past history, hopefully James Webb will far exceed that time frame. Now let me stop sharing that screen, and I will share this. If you are interested in James Webb, let's do that. This is, if you go to YouTube and just type in JWST, you'll get this particular video, which is a live feed. It basically tells you all the things that you would want to know about where it's currently located, how far it is away from Earth, how far away it is from the L2 orbit. I'll talk about what that means in a second. It's what's the percentage of distance away and what its currently cruising speed is. The key thing to note is that the JWST is fully deployed, in the sense that it has unveiled itself, and I'll show a video what I mean by unveiling itself. It's actually an astounding feat of engineering. It had 344 I can't remember what they actually called it, fault points, or there were 344 chances for the telescope not to be deployed correctly. Essentially, 344 actions had to be taken in order for this telescope to be fully operational. So it is an amazing feat of workmanship. But before I get into that, I want to talk about a naming. JWST is not without its controversies. So let me do this. Where did I put? There we go. Eventually, I'll learn how to tech efficiently. Or not. All right. Once more with gusto. So the JWST, the actual, what that stands for is the James Webb Space Telescope. I personally that is the last time you will hear me refer to it as that. I disagree with naming this telescope after this individual, and I'll explain why in a moment. So I will refer to it as the JWST. The reason why this is, well, first let me describe this gentleman. He is a NASA administrator. He was the let's see if I have the dates somewhere around here. He served in government since 1949. From 1949 to 1952, he was an Undersecretary of State. And that is a fairly crucial time. And that is where the controversy started. From there, he was the NASA director from 61 to 68. He was the NASA director during the beginnings of the Apollo program. And he was the one that spearheaded Mercury, Gemini, and the beginnings of Apollo. And so without James Webb's being at the helm, we would not have won the space race, as it were. We would not have the space program that we do today. So he is. So in that sense, he is definitely a gentleman of note and acclaim, and should be celebrated. He was also responsible for the integration of African Americans within the NASA NASA family. He would why am I losing my words? He would take trips to the South and recruit promising engineers and physicists from the Southern historically black colleges, and he would bring them to NASA and incorporate. So, from a civil rights perspective, he was again also fairly was a visionary in that term. However, the controversy comes in when he was an Undersecretary of State, now under Nixon. Now, Nixon is notorious, and the Nixon administration was notorious for being homophobic. During the Nixon administration, there was something referred to as the Lavender Scare, where the U.S. government actively tried to find and weed out homosexuals. Hundreds of homosexuals within the government were discovered and fired because they believed that homosexuals were a security risk. The idea is that these folks were hiding a part of their identity, and they could be Russian or Soviet assets could find, if they found out about this, their secrets, they could use them to exploit these individuals for espionage gain. It's ridiculous, and like I said, homophobic. Really, I believe the main motivation is they just didn't want them in government, and so there was this started when documentation came out. There was a meeting during Webb's tenure as the undersecretary, and unfortunately, the memo that was created was actually misattributed to him. Excuse me. Scam Likely keeps trying to call me. I keep telling Scam we're over, but he keeps calling, and I don't know. Anyway. So the document was misattributed to him, and the document was very direct in its implications of seeking out public records or government records of federal employees and firing them. I believe half a dozen of them were actually eventually found and fired from NASA. So this had a significant impact on the homosexual population, and so they were unduly persecuted because during this time. Now, and when this document came out, and when it was originally attributed to him, there was a large outcry to rename the telescope after someone else. Even though he had these accolades as the NASA administrator and was a proponent for civil rights within NASA, the fact that he was allegedly the author of this homophobic memo really should have disqualified him from what will become a household name. Very much like Hubble will be part of the zeitgeist in terms of space exploration, James Webb will take over that role. And so it was felt that despite his accomplishments, he should not be given that sort of recognition. There are many astronomers, particularly female astronomers, that could have been chosen as more appropriate to name this pioneering telescope afterward. However, like I said, the memo was misattributed to him. It was actually another undersecretary whose name I cannot, for the life of me, remember at the moment. It was not James Webb who wrote it, but it's still felt that, as I said, the Nixon administration, this was widely known. This was widely known that they were doing this, both in all manners of government. James Webb's proponents will argue that there is no direct evidence to suggest that he was an active member of the Lavender Scare, but his opponents, such as myself, feel that he had to know. This was such a pervasive attitude in government that there was no way, particularly at his level of his rank, as it were, there's no way that he could have not known this was going on. Again, this is a very gray area, but in my estimation, the reason why it should have been renamed was that there are so many other astronomers who don't have this baggage associated with them. James Webb can be celebrated, should be celebrated for his contributions to NASA and astronomy in general. I just don't believe that he needs to be. This is how we celebrate him. So there was that. There was also part of the controversy where NASA did acquiesce and investigate this. However, and they said the investigation ended up the final judgment was that there is no, like I said, direct evidence that James Webb either knew about this policy or implemented this policy. However, NASA did not make this investigation public. It is or transparent. So we do not know what they investigated, what sorts of resources they used to actually look into this. We do know that they did not look at the Nixon Library, which is obviously a large repository of memos and papers during Nixon's administration, which would have pointed to who knew what and so forth. So, one, NASA's investigation was not transparent, which pissed off a lot of people, and it was certainly not robust. It was certainly not exhaustive in its approach. The other problem with the James Webb Telescope is that it costs a lot of money. The final budget for creating this thing and putting it in orbit is around $10 billion. To give you a sense of scale, all four of the previous observatories that I talked about, those were built for $10 billion, roughly speaking. The other problem that it had was that it was originally slated to be launched in 2018. That was pushed back to 2020, and that was pushed back again to 2021. I actually was of the impression that that JWST was actually a hoax, that basically weren't actually going to put it in orbit, but lo and behold, they actually did. Eventually. There were a couple moments where essentially the project hemorrhaged money. It was mismanaged, and it was potentially going to be cut due to how the budget was being used. And like I said, $10 billion in terms of NASA's budget is a pretty good chunk of change. Unlike what certain people will say, and say, talk about how much money NASA has per year. NASA's budget accounts for around 0.1% of the total U.S. budget. And there are also complaints that that $10 billion could be better spent funding social programs and so forth. Personally, I think that we can walk and chew bubblegum at the same time, particularly given that our considering the hundreds of billions of dollars we spend every year on military expenditures. I think maybe we could cut a slice of that pie off and use it for social programs. But that's a conversation in and upon itself. The point is, it's a bloated budget. It was just mismanaged from a financial standpoint. But those are the controversies. Now, what is it going to give us? Well, it's going to give us quite a lot, actually, hopefully. Let me do this. I want to, while I'm talking about it, I want to, whoops. Pause that for a sec. put myself there, and let's just start this. So this is an animation which shows you what the how this thing is deployed in this compact formation. The reason why it was so why it's so compact is that it had to be put into the nose cone of a Adrian. I forgot or have it an Adrian 5 rocket, and so because the telescope's mirror is 6.5 meters in size, and you can see that it is hexagonal in shape. The reason for that is large telescope mirrors, all large telescope mirrors, it's impractical to, yes, Dora, that's the Adrian 5, yeah. It is impractical to create mirrors that are larger than, say, 5 meters at this point, because the precision to which you have to grind them is ridiculous, and it takes a really long time to grind them. And the other process is actually to spin mirrors, where you have a liquid glass and you spin it, and basically due to centrifugal forces, the rate of spin will give you the shape that you want. But even still, trying to spin up a 5-meter dish or 5-meter mirror is, again, impractical for a number of different reasons. I am going to start that over. So modern telescopes, the larger telescopes, are created out of hexagonal mirrors, basically around 1 meter or so, or maybe a little bit smaller. Hexagonal mirrors, very much like a honeycomb. These mirrors are much easier to manufacture, and you can put them together in order to basically construct a much larger telescope. And there are other reasons why that there is an advantages to creating telescopes in that way. But you can see that this is somewhat. There are a lot of things that could have gone wrong, and I may have mentioned this before, but there were 344 points at which the telescope could have failed in its deployment. So thankfully, none of that happened, which, again, I am just friggin' amazed by. So what can Hubble, or what can James Webb do? And I will pause this. What can James Webb give us? Now, James Webb's mission is essentially twofold, or at least, again, it has two major goals that it wants to look at. The first, of course, is exoplanets. The second is galactic formation and cosmology. Now, you might hear that JWST is the successor to Hubble. That's actually pretty inaccurate. It is the successor to Spitzer. And I'll point out, and if I have time, I will point out why that is problematic going forward. It is primarily an infrared instrument. While its technical range goes from 0.6 nanometers or 0.6 microns, which is in the visible range, to 28.5 microns, which is definitely in the IR. The visible part of the range is only used by the fine guidance sensors, which are used to basically position the telescope or point the telescope very, very precisely, so that your target of interest is actually in the telescope's field of view. Now, Hubble has made use of the fine guidance sensors in other ways, in actually taking images and making studies that way. And so I would anticipate JWST is going to do the same. But its science instruments, its four major science instruments, are all infrared. And they're all designed to move into the infrared. And so it has also been equipped with what we call a coronagraph. Now, again, like I said, I'm hoping to be able to make a video which talks about exoplanets, how they're discovered, techniques that are used to discover them. But a coronagraph, simply put, is a sun shield or a star shield. Looking at finding exoplanets or studying exoplanets near a host star, it's very much like trying to study the light from a firefly right next to a flood lamp. It is the magnitude differential between those two things is enormous. And so one of the techniques that we use is literally stick a blocker where it blocks out the sun's light, so we can actually study it. Now, JWST is going to have a precision down to, or an angular resolution down to 0.1 arc seconds. That is 10 times better than Hubble. And so with that, it'll actually be able to do similar things that Spitzer was able to pioneer, primarily exoplanet atmosphere research. With the any idea on the correction rate at LG2? I don't know, Dora. I don't know anything about the correction rate at LG2. I will look that up for you at some point. But the JWST is going to allow us to look at a larger number of exoplanet atmospheres. And primarily, what we're going to try to do is what astronomers are going to do is they're going to look for what we refer to as biosignatures. If we see oxygen, for example, or water vapor in these atmospheres, that is a good sign. That is a piece of evidence to say that planet is habitable. There is some speculation as to if you see carbon dioxide at certain levels, that actually indicates a certain technological advancement of this world. So it might be that these planets are inhabited, but that is very tenuous. That is very speculative at this point. At the very minimum, JWST will be able to look at planets and determine whether or not, at least to first order, that the planets are habitable or capable of supporting life. I don't believe it is going to be able to really give us any pieces of information to say that any of these planets are actually habitable. It will also help us with determining just the bulk characteristics of exoplanets. Because at the moment, if you look into exoplanets, you'll hear about Jupiter-sized planets, Earth-sized planets, that sort of thing, gaseous worlds, rocky worlds, and even water worlds. But the evidence pointing towards these different types of morphologies or compositions of worlds is very model dependent. The precision of the measurements that are being used to find these, to basically determine the densities of these planets and therefore what these things are composed of, the error bars are fairly large. And so what's hoped with JWST is that the observations will be able to greatly decrease these error bars that will allow for larger or better density measurements, better mass measurements, better radii measurements, and better density measurements, and will actually allow for more detailed modeling of what these worlds are and what they're composed of. One of the more exciting things that I'm interested in is that we have evidence at the moment of planets that we haven't been able, that are not in our own solar system. Right now, our solar system is basically half terrestrial rocky planets or half gas giants. There is now evidence that suggests that there are planets out there in the galaxy or out there in the universe that are almost entirely composed of water, that are essentially water or liquid worlds. So Kevin Costner might actually be onto something, except for a good movie. That he's not. Yeah. So JWST will definitely be able to expand our knowledge, expand our inventory, as it were, of exoplanets and their physical characteristics. The other thing that's going to study is cosmology, and that's going to do it in two ways. Well, let me back up for exoplanets. The other aspect of the exoplanet research is that because again it's in the IR and it has a high angular resolution, we can now probe deeper into these uh, clouds, and we can look at these young stars and the disks surrounding them. Disk is a material that where planets form. We're able to study them with much greater precision than we were able before, and we can improve our models and our understanding of how these stars come together and how planets form. It'll hopefully answer some of these more nebulous questions, such as do stars typically form in as single objects, and then at some point in their early history turn into binaries, get to clump together with other stars, or do they form as binaries? Stars are social creatures. Half of the stars that are in the night sky have companions. Either they're two stars orbiting around each other, or multiple stars orbiting around each other. So there has to be some kind of mechanism that gets these stars together, some kind of stellar Twitter or stellar Tinder, as it were. And we want to. So the open question is it something that happens prenatal, or is it something that happens after formation of these planets? So JWST is hoping to be able to answer that question. It will also do a statistical survey of galaxies and galaxies from a range of ages. It will be able to look further into the past and be able to. We're looking at galaxies that formed at millions of years rather than billions of years, and so we can actually look at galactic formation. We can actually have observations of galaxies as they are forming, because that is not something that we are able to do currently. We can model what how galaxies came into being, but we do not have any observations of essentially a prenatal galaxy or a proto-galaxy. And so JWST is going to allow us to make direct observations of proto-galaxies, and it will also be able to tell us when these proto-galaxies actually form, because again, that is an open question. Because at some point during the history of the universe had matter in it, had hydrogen, helium, and all that sort of stuff, but it had no large cohesive structures like galaxies. So trying to understand how long or what that time frame is, JWST is going to be able to clue us in on. And it's going to probe a region known as recombination, an era known as recombination. This is when these heavier elements form. These electrons got trapped around protons, formed hydrogen, helium, lithium, and a little bit of lithium. And we know, roughly speaking, it happened around 380,000 years after the Big Bang happened. But again, it's very model dependent, fairly large error bars. As you can tell, we only really have two significant figures to that number. So JWST is actually going to be able to probe down to those timescales and allow us to have a much better or much clearer understanding of when these elements started forming and came into existence, which in turn will help constrain the overall Big Bang cosmology and really constrain the age of the universe and things of that nature. So those are the main goals. And there are a lot more goals that I haven't talked about. Those are the main goals of JWST. And so it will revolutionize the field of astronomy as we know it. It will allow us to probe regions of investigation that we currently do not have the technology or ability to do. Oh, one thing that I wanted to mention is that where it's going to be located. Now, it is going to be located, or is located. I'm going to kill that. In what is known as the second Lagrange point, or L2. And actually, it's going to be in orbit around the Lagrange point. I have too many tabs up. Oh, that's not a tab, that's a window. That would help. There we go. Share. Hey, I've got bots. Welcome, Euphema Cuisine. Anyway, so there is these things called Lagrange points, and I'm not really going to go into a lot of detail about what these actually are. But what I will say is that they are places of stable equilibrium. So imagine that what you're looking at is in a rotational frame, meaning that the frame or this image or this configuration is rotating at an average speed of however fast the Earth is rotating or revolving around the sun. I don't keep that number in my head. So if you were rotating at that speed, you would see the Earth and the sun basically fixed in that rotation frame, and then the moon would be rotating around the Earth. If you look in that rotational frame, there are 5 different positions that are stable, meaning that if you put an object in those points, it will stay in those points. The gravitational attraction between the sun and the Earth will basically keep that object in the rotational frame at that position. And some of them are more stable than others. One of the more sort of popular examples of Lagrange points is actually Jupiter. If you Google about Jupiter, you will find that there are asteroids which precede and trail Jupiter in its orbit. Depending on who you talk to, these are just the Trojan asteroids, or one side are the Greeks and the other side of the Trojans. I can't remember which one's which. But these are in the L4 and L5 positions. So these asteroids are basically kept in that region of space due to the gravitational influence of Jupiter and the sun. The Earth has these similar points. And JWST is going to be in orbit around the L2 point. So it's going to be currently, let me go back. I think it's at 1.5 million kilometers at this point. Yes, it is currently 1.45 million kilometers away and is currently cruising at the so fast speed of 0.2 kilometers per second. So, yeah, it's getting there. It'll probably get there in the next, week or so. I actually don't know. I'll let somebody else figure out that math. It is 99.77% to the L2 orbit. Now, the reason why it's in the L2 orbit is basically 2 reasons. Three reasons. One, it's a stable point. It's a stable position, so we don't have to expend a whole lot of fuel or what have you to keep it in its orbit. It's not in the way of. Basically, and the other point is it's not in the way. So it won't clutter up this basically increasing space community of satellites, particularly Elon Musk's and Bezos. Don't get me started on all that. I despise Starlink and Elon Musk to a certain extent. But anyway, where was I? So yeah, it basically will keep it out of that mess, and it will also keep it away from the Earth. And so the Earth is, it's warm, and it is a contributor to the IR part of the spectrum. So having it 1.5 million kilometers away minimizes the contribution that the Earth would have to sort of background radiation that the thing has to deal with. So right now it is in what's known as the L2 insertion burn, where it's going out and it's going to put itself in orbit around this position. So With that said, where did it go? Do I have a picture of it? I don't know if I have a picture of it. I don't know if there is a picture of it. So let me stop sharing um, and I'll end this with talking about the future. So JWST, like I said, bloated budget, mismanaged, but it finally got launched 3 years after its initial conception. Real quick, Dora asks, can I put this up here? Dora asks, how often do you guys spot Starlink sats in your images? Uh, I do. I honestly don't know how often it happens, but it does happen. It happens with enough regularity that that is becoming a nuisance, particularly with use in wider field, larger telescopes that are able to actually see these things. Um, I know the Gemini telescopes, which are zero point 0.8 meters. One of them is in the south. There, you can Google. There's an image where it's just basically ruined by by about a dozen streaks across across the chip, which corresponds to the Starlink. And at the moment, I haven't checked on it, but at the moment, I believe there are a few thousand Starlink satellites up, and the plan is for tens of thousands of these little to be launched. So it's only going to get worse from here as to how it's going to contribute to astronomical observations. From what I gather, there are going to be essentially, or we're going to look at, we're going to in words. There are going to be basically null or zones of avoidance where telescopes will have to basically not be able to point in certain regions of the sky because they're going to get interfered with satellites, particularly with Starlink and whatever Bezos is going to call his constellation. So JWST is a marvelous feat of engineering, but it took a Herculean effort to get there. The next observatory in the next generation space observatory is what was previously known as WFIRST, is actually now known as the Nancy Grace Roman Space Telescope. That's going to be a mouthful. She was also a NASA administrator. She was the first female NASA administrator first woman NASA executive officer, as it were. She made her bones, unlike James Webb, who was a politician. Miss Roman, or Dr. Roman, was an astronomer. Primarily, her field of study was stellar classifications and movements. The Roman Space Telescope is scheduled to be launched no later than May 2027. So 5 years. 5 years, give or take. And that's the proposed date. Again, if past this prologue, we have James Webb was not launched on time. So there is a certain expectation that Roman will not be launched on time either. Roman will also be put at the L2 position, basically get out of there, get it out of the Earth's orbit. And its budget is a modest $3.9 billion. Now, the Trump administration has already tried, or the previous Trump administration has already tried to kill it because of the cost. So, while right now it has been renewed, and I can't remember. I think it was 2018, 2019. Congress actually made some promises, some assurances that the funding will flow. Spice must flow. The funding will flow, and that Roman telescope will fly. The difference between the Roman telescope and the JWST is primarily field of view. JWST has a modest to small field of view, so it can only study a few objects at a time. So it is a much more targeted instrument than Roman. But again, Roman is going to be primarily infrared. It does go into the visible, but I don't know at this moment. At this time, it's still in a fairly early development stage, so I don't know what the actual instruments on it are going to be and what they're primarily going to be used for. So, like I said, with JWST, while technically it actually goes into the visible part of the spectrum, it is primarily an IR instrument. The Roman telescope is also going to be a infrared instrument. Again, it is theoretically a 5-year mission, and it's because of its wide field, it is primarily going to be used again for exoplanet and cosmology. Those two seems to continue to be the sexy sciences. It's going to probe dark energy. Not entirely certain how it's going to do that, but that is one of the stated science goals. And it's also going to look for exoplanets. JWST will study already found exoplanets. It will not find it in upon itself. It is not an instrument designed to do that. Well, designed and also meant to do that. Dora, I didn't even bother seeing it because I don't like the director, and yeah, I don't like the fact that it's 2 movies. But that's like I said, it's completely off topic. So Roman telescope will actually increase some statistics in with our exoplanet population, because while we've found thousands of these, because of the limitations with the telescopes that are being used and the methods being used to discover these planets, there are gaps in our knowledge. For instance, trying to find an Earth that actually is at the distance from its host star that we are, we don't have a lot of capability to find those planets. We can't find Jupiters that are farther out in where Jupiter is at 5 AU, for example. So there are gaps in our knowledge of finding these planets. So any conclusions that we're currently making about the formation of exoplanets and the statistics of how many exoplanets are gaseous versus terrestrial, they must be taken into account that we do not have a full sample. And so Roman is going to actually use a technique known as microlensing. And so gravitational microlensing is when you have a luminous source in the background. Let's see here. You have a luminous source like a galaxy back here, and you have some massive object moves in front of that luminous object, or more luminous object. And what that does is because the light is going to be bent, because relativity tells us that light bends around mass, the light from the luminous object is going to bend around the mass of this intermediate object. And that causes what we refer to as microlensing. We get these arcs of images of that background object. As before, I will go into greater detail talking about that technique later on. You can use the same technique. Primarily, microlensing has been used to look at galaxies because they're very, very luminous, and looking at very large masses because of galactic clusters. But you can use it for planets. The luminous object would be the host star, and the planet would be moving in front of it. Well, essentially, yes. And what that does is that part of the microlensing event will cause the background object to become amplified in its brightness. And based on that signal, we can determine the mass of the intervening object, if it's planetary in size, if it's not. And so These are the problem with microlensing, trying to find microlensing events, is they're not repeatable experiments. They're one and done. The planet is going to pass in front of that background star, and it's never going to really come back again. So what we have to do is we have to do these wide field observations in order to get enough stars in the field of view that we can just serendipitously discover these things. And the reason why microlensing is cool and fun and a nifty party trick is that it will help it actually can probe some of these spaces of stars, of exoplanets that we haven't been able to probe before, primarily planets at distances that we see within our own solar system. Hello, George. But then that leaves us with the absolute future. So, or with future beyond that. And so the 2020 Decadal Survey, again, you guessed it, exoplanets and cosmology. And they basically only were going to, or they pointed out, or primarily, or basically, they want funding for for another telescope called LUVIAR. This is still in the, right now it's in the we want money phase. It isn't even in the, there are a couple of versions of this space telescope out there. There is a 8-meter there is an 8-meter version and a 15-meter version. Again, these will look for exoplanets, dark matter, and oddly enough, it'll be the first major telescope, major observatory to actually have as part of its main mission statement to look at solar system objects. So to see whether or not there are large objects, Pluto-size objects out in the Kuiper Belt and whatever, what have you. And so the LUVIAR is going to be, but again, if past this prologue, with a number of these space telescopes, particularly with the ones that I mentioned before, the 4 great observatories, a lot of these were downsized, or the instruments were taken off, or what have you, from initial conception to launch. It's just a natural consequence of budgetary concerns. And LUVIAR is going to be A, expensive, and B, it's going to be downgraded. It's probably going to be what we refer right now. What's being kicked around is LUVIAR Light. It's probably going to be the 8-meter telescope. The issue with this is that this will be a true Hubble successor. This one will actually observe in the primarily in the visible range, although it will cover some of the IR. There are a couple of other telescopes out there. There's HabEx, the Habitable Exoplanet Observatory, that will look for biosignatures, primarily look for biosignatures. There's the Lynx X-ray class, which is the Chandra successor. And then there's the Origin Space Telescope, which, yet again, will be in the infrared. The problem is, at this point, HabEx, Lynx, and Origins are speculative. They weren't in the Decadal Survey. They weren't mentioned in the Decadal Survey. So at the moment, we are not looking at funding these missions. We're not prioritizing the astronomical community is not prioritizing these missions as missions that need funding. And LUVIAR is expected to, and the launch date for LUVIAR, I know I had this written down somewhere. Oh, the projected start date of actual develop of construction is 2030. With previous space telescopes, you're looking at least 10 years before you can, before it's going to be able to be launched. So we're looking at the next major telescope around 2050. Or 2040 or so. These other telescopes, if they actually happen, are going to be around 2040 to 2050. Which brings me to the 2 problems that I have, or the two points of concern from the for the astronomical community moving forward. Fairly recently, or fairly soon, Hubble and Chandra are going to stop working. When Chandra goes, we will be blind in the gamma and X-ray regions of the spectrum, and we will be blind for gamma ray and X-ray science for an indeterminate amount of time. As I said, the one telescope that's currently on the plan is Lynx, but that's, again, it's speculative. We don't know whether or not it's even going to get funded, if it's going to go beyond the idea stage. So it's not guaranteed in any way. And even if it is, that's going to be 20, possibly 30 years down the line. And so there are going to be decades where our understanding of high energy science is going to be exceedingly limited. So if you want to study things such as supernovae or black holes, particularly interactions of matter around black holes, if you want to study the evolution of black holes, you're kind of out of luck. You will be kind of out of luck because, again, NASA is not prioritizing these missions. It is putting it seems to be putting a lot of its, or all of its eggs into one basket. It is, instead of doing multiple smaller missions that cover a wide range of wavelengths like they did with the first four grand observatories, they are basically prioritizing one telescope at a time, which is, like I said, it's going to be problematic because it's going to limit our ability to, while we'll have these very nice observations within, say, the IR, and a lot of things will be discovered. It's not the only wavelength regime, and there are going to be a number of astrophysical objects that are going to be, or phenomena that are going to be overlooked, as it were. Now, in a second, I'll sort of address that point. But the other concern that I have is, again, by putting all the eggs in one basket, we've already seen with previous missions that the funding is going to depend on administration. Like I said, the previous Trump administration almost killed JWST. Hubble at one point was in danger of losing its funding. And so who knows? Chances are the Republican Party is going to win back the House and the Senate in the midterm elections. And as scary as it is, they may take back the White House in 2024 with either presumably Trump or possibly DeSantis. And bye, Tux. I won't be too terribly long with this, but so you won't miss too much. But so who knows? So these are, because it is going to take so long to develop these missions, and these missions are going to be so very expensive. There are a good chance that they'll just get cut. There's a good chance that they won't fly. The Roman Space Telescope also nearly lost its funding a few years back, but thankfully it's gotten its funding back. So those are the two primary concerns that I have with space telescopes. Is that, it's going to be very slow going. They're going to be very narrow in their focus, and they are tenuous. The missions could very easily go away because the funding is just simply not there. Particularly in this, because not only do Republicans not want to fund science, or fund, well, probably science, but definitely not fund astronomy or space science. We also have sort of the newly opened ideas of going back to the moon, potentially putting industry in space with multiple space stations, There is a pie in the sky idea of doing asteroid mining. And so the limited budget of NASA may be diverted from exploratory missions to more industrialized missions. But again, that's speculative on my part at this point. But that is one of the fears that I have. So you might want to. So the last point that I'll make is you might ask, Rob, what about ground missions? What about ground telescopes? Well, we have kind of a problem with that as well, in that. Let me back up a second, because right now I've been being very U.S. centric, which is don't want to be. That's a problem that we have here in the States, is that we get accused of really not paying attention or giving credence to anyone else. And so there are a couple of missions. Euclid is one. I believe Euclid is going to be an X-ray as well. But as far as I know, the European Space Agency is not going to be, doesn't have large space observatories in the work. I could be very wrong about that, but as far as I know, NASA is going to be the spearhead for creating these large space telescopes. So maybe, hopefully, the Europeans will realize that this is bullshit, and they will actually create telescopes in the gamma and the X-ray. But what about ground-based telescopes? Again, running into a problem of putting all of our eggs in one basket. Right now, the largest ground-based telescopes, as I said, are Keck. Now, the two Keck telescopes, the two 10-meter telescopes. There are half a dozen smaller telescopes, 8-meter telescopes, and they are doing phenomenal science. And they will continue to do phenomenal science for years to come. And so there are two major telescopes in development, the TMT and the ELT. The TMT is a U.S.-based project. It is and this is a lesson in just how imaginative astronomers are at naming things. The TMT stands for the 30-meter telescope. So this is a telescope that's going to jump from 10 to 30 meters in size. But the problem is, we don't know if we're going to. The project has been stalled, and not for financial reasons. It's actually been stalled because of the fact that NASA can't be trusted. This is a much longer story, but ultimately, the original site, or the primary site for the TMT, is Mauna Kea. Mauna Kea is perhaps the best observing site in the world for various reasons. There are currently, I think, 16 telescopes on Mauna Kea. Problem is that Mauna Kea is parts of the summit are holy to Native Hawaiians. And we have continually told them, we're done. We are no longer putting telescopes on there. Or if we put a telescope up there, we're going to take one down. We're going to take one out. And very much like the U.S. policy with indigenous peoples, we're basically lying to them. We haven't actually done that in any way. And so you may have heard, it actually got the attention of Jason Momoa, The Rock. There was actually a protest which shut down the summit. So telescopes actually had to shut down observing runs because they couldn't access them over protesting putting the TMT there. I don't know what I haven't looked into this so far or recently, but the idea is either somehow we need to accommodate or come to an understanding with the Native Hawaiians, or there is a secondary site in the Canary Islands, which is not ideal, but you can put it there. Do they have it in writing? I don't know. I don't know about the details in that. I do know one of the concessions that we made with the Native Hawaiians is that we created essentially an institute on Mauna Kea, which highlights Native American or Native Hawaiian culture, things of that nature. And theoretically, we're supposed to be naming astrophysical objects after Hawaiian gods and so forth. Oumuamua was part of that endeavor. That the comet that came in, or the asteroid that came in from interstellar space, that was named Oumuamua as a sort of olive branch to the native Hawaiian people. I personally have some issues with that, or with I don't think that's enough. I think that's basic, almost insulting in my view. But so you have the TMT, and theoretically that's going to get built at some point. But until then, there are no major ground-based telescopes being built. So we're going to be hitting a limit, and we are certainly hitting a limit with the sort of projects that we can do with these larger telescopes. Now, I don't know how many people are in the chat. It tells me 9, but let's see if you can figure out what the ELT, what does ELT stand for? What is ELT an acronym for? What do you think that stands for? We'll wait a few moments. The ELT is a European project, I can never get it straight if it's ESA or ESO. I think it's ESO. It's an ESO project, European Space Organization. And it's going to be 40 meters in size. Close. James, you're close, but not quite. You've got 2 of them right, but not quite. Damn it, Scam. I told you it's over. Is it the ESA? Okay. I know, again, I could be very wrong about this, but from my understanding, one of them is space-based, the other one is ground-based. So the ELT is 40 meters. And as far as I know, that's still in the development stage. I don't even know where they're going to put it. But yeah, I don't know of a hard, firm deadline as to when that's actually going to be built. If it's going to be built. Nope, not European's large telescope. That's getting further away. I'll give you guys one more guess to ELT. So again, astronomy is hitting a wall, in that we are sort of getting pigeonholed, or basically, like I said, putting all of our eggs in one basket, and we are limiting the instruments that we need to do science. Because astronomy is largely a observational-based science, if we don't have the observations, we can't do the science. And I fear that is going to limit our ability to understand the universe further on. George, you got it. The Extremely Large Telescope, ELT. It goes along with such wonderful names as the VLA, the Very Large Array, the VLBA, which is the Very Long Baseline Array. So the VLTI, Very Large Telescope Interferometer. So yes, we are exceedingly ingenious with our naming systems. So my semester starts today, and so there are things that I need to take care of, but I will stick around for a little bit if folks have any questions or opinions as to the state of things, or if you, like I said, you had questions about what these telescopes are going to do, or anything I've talked about. So yeah. Next week, I am definitely going to have knock on wood, I'm definitely going to have a Coffee and Science. As I've mentioned in other streams and other places, I'm hoping to get Maddie from Science Side Up here And Professor Phil Bell, if he's in the audience, I'm going to email you, and hopefully you will be amenable to coming on so that we can chat about science and science nihilism and so forth and so on. There are a couple of other folks on YouTube that I plan on reaching out to as well, and then there are colleagues of mine that I will try to reach out if they have the time to do that. Okay, well, thank you all for watching this. I am always amazed that anyone wants to hear what I have to say. So thank you again. And just as a sort of channel update, I will be, for those who are interested, because of this new semester, I will be putting out bi-weekly videos on basically lectures. I will be doing my lectures online. And hopefully this semester I will be better at finishing off the rest of the semester by doing them all online. So watch out for those. I also, in addition to interviewing or having conversations with colleagues, I also am going to be putting out feelers with flat earthers and trying to. I'm basically going to mooch off of MC Toon, and I'm going to look at the folks that he has debates with, and then I'm going to reach out to those folks and see if they want to come on and have a conversation. Rachie, if you're still on, I really would like to have you on so that we can have the conversation. These conversations with the flat earthers are not debates. I do not intend to debate people about what the shape of the earth is. There are plenty of avenues for people to do that. What I'm interested in is why folks have this belief. Why is it that they essentially reject expert opinions on this? So I would very much curious as to why these folks have the opinions that they do. So I will be, hopefully that will be also a continuing series. And lastly, periodically I will be creating sort of debunking videos. I've been hesitant to do debunking videos in the past, but I feel that it is important for me as a man of faith to look at young Earth creationism, particularly from an astronomical point of view, and to refute it from both a scientific and theological point of view. So yeah. I will reject your reality and substitute my own. Yeah, that's kind of the feeling that I get. But yeah, it's been great blathering on. And so until next Sunday, peace out. And remember, no matter how dark it gets, you are stardust.